have my name tag on, but I'm Peggy. You'll know me because I'm the one with the crutches. We have a couple new folks. We have a couple of folks who weren't able to make it to the watershed tour on Tuesday, and we have a couple of folks who actually just joined us today. We talked them into it, I know. My prodigious powers of persuasion. So, Jabari and Terry and Mike, would you just give us a quick introduction and tell us who you are? No, that's all right. Come on in. There's a sign-in sheet in the back and name tags. Okay.
Thank you.
Just stand up and kick it off. Hi, welcome.
Well, I'm Jabari. I don't know what the...
Where you living? What?
Well, I stay in South Minneapolis on 33rd and East Lake Street. I am currently enrolled in Vermillion Community College, which is 255 miles north towards Canada.
It's a long walk each way.
Yeah, and I plan on achieving my associate's degree in water quality science in 3 years, and then get my bachelor's within the next 4 years.
Excellent. Hey, thanks. Welcome, everybody. And Mike?
Hi, I'm Mike McCabe, and I've been retired a year. I was a librarian with Hennepin County and worked with the Minneapolis Library since way back. And this is a thrill for me to find out about this today. I've lived around the creek all my life. I grew up in southwest Minneapolis, where I'm living now. So pleased to be, well, happy for the opportunity.
Thanks. Welcome.
Terry? I'm Terry Hammock. I'm also live close to the creek and on the site of the former Page School, and there's some townhomes there now. And I've lived in southwest Minneapolis or that area for the last 30-some years, and I've been retired a couple of years after working as a healthcare social worker for several decades.
Welcome. Thanks for being with us. And Lily, do you want to introduce yourself as well?
Sure, thanks. I'm Lily McMillan. I'm a board member of the Freshwater Society, which is the Freshwater and the Minnehaha Creek partner together for this program. So I want to thank you all in advance for putting in this time on behalf of the water issues for our community.
And you have a day job.
Yeah, I am mayor of the city of Orono as well. So, but, freshwater is as important, believe me. So I appreciate all the effort that you're all putting in right off the beginning.
Well, welcome. Thank you for being here. Hi, welcome. Come on in. And this is our newest. You're going to just put you on the spot right there where you stand. This is like the test by fire. So introduce yourself.
Hi, I'm Rosie.
And you are here because you are the newest intern at the Freshwater Society. And you live around the corner from me, which is just like you.
I know.
We met out in Anoka. I'm like, you live in Corcoran? That's where I live. So welcome.
Where should I sit?
Right here.
Okay.
So welcome, Rosie, too. So Rosie will be going through the whole certification process with you. So welcome, everyone. Our final introduction is Diane Specker, who will be our instructor today. Diane, would you just give her a quick introduction to that?
Hi there, thanks to all of you for participating. I'm really happy to be here. And
Welcome all. There's name tags and the sign-in sheet, so help yourself.
so that we got a full house, which is great. Just a little bit about me. I'm actually a water resources scientist for Wank Associates. We are a environmental engineering firm. And I'm part of our water resources group, which is a group of about 30 people in our firm that work together to solve water resources problems. We work a lot with watershed organizations, watershed districts, soil water conservation districts, counties, and lake associations, private enterprise, just really a wide gamut of clients. Myself, I work almost entirely with public sector clients. Almost all of them are watershed organizations or cities or counties. And I work all over the state. Last week I was down in Dakota County working on the Vermillion River. Today I was out in Independence working on Pioneer Sarah Creek. Next week I'll be up in Ewing working on the Kawishawee watershed. Some of you may have noticed just recently that the Kawishawee River was designated by American Rivers as being a potentially threatened water resource based on the discharge from mining operations and from the plant expansion. Well, we won't get into that here, but
No, but I mean, they haven't started any mining, that's what I mean.
yeah, there is mining up there right now. There are some impacts coming from the mining, but not nearly what it could be. So I'm kind of all over the place. I specialize in stream ecology, so I like to jump into streams and pick up bugs and count the fish and do things like that. I also do a whole bunch of other stuff. A lot of what I do is work together with organizations to help them plan, to diagnose what's going on with their water resources, come up with some ideas for what to do to improve those, and then help them either design it or find the money for it, or just move them along the way to actually implement those improvements. I'm going to be talking today. This is kind of your first real dipping your toe into the water. A real fundamental building block of what you need to know to be certified as a water steward. Hydrology 101. A lot of what I'm going to be talking to you about today.
Before we get into the content, I just want to take a pause quick to make sure everybody has a journal. Raise your hand if you need a journal.
If you need a journal.
Specific journal. So we've got, I just want to make sure everybody's got what they do. Are you going to share? You should have enough journals. We need one up here. Oh yeah, it is a fancy shirt. Oh, let's see that. And did everybody get a packet with all of the syllabi in it? Carlos, I know you needed one. Would that have been the same packet that was in the...
Yep, same one.
Oh, what packet? I mean,
I gave you everything.
All right. So we all good?
Before we leave housekeeping, restrooms are down the hall. Drinking fountains right up here. You want a penny if you get it and walk up.
This funnel here?
Go straight that way.
That way.
Yep. They're down at the end, by the council chambers.
All right. Thank you.
Okay. So this hydrology lesson is based in part on a lesson that I have done for the past 5 years in a summer program with high school students from Patrick Henry High School in Minneapolis. So if high school students can absorb and learn this lesson, you can too. So just because this looks like it's been hydrology, oh my gosh. What I want to achieve tonight is for you to understand some basic concepts, understand some terminology that's used, and get kind of a basic understanding and a preparation for what's going to be coming to you in the following lessons. So that you have some really basic understanding. So when 3 lessons from now somebody talks about a 100-year event or a hydrograph or a hydrologic soil groups, you'll know what they're talking about. Okay, so you may not have 100% knowledge of everything by the time you're done here, but at least you will have heard the terms. And you'll kind of have a basic understanding of it. So if you had a chance to look through the syllabus, you'll see that we suggested that you bring something to this class. Somebody remember what that was, and if so, did they actually do it? So we asked you to watch the newspapers and bring to the class an article that you saw that had something to do with water, specifically quantity of water. Anybody do that?
It's a precipitation.
Precipitation?
Yeah.
Okay. So I'm going to put about 3 of you on the spot right now. Can you tell me just a little bit about the article, what it is that caught your attention about it, and what more you'd like to know about it?
Sure. So with precipitation, went kind of the snow route and was thinking about the drought last year and how all the snow would impact that and have a positive effect on, taking away the drought did last year. So I found an article that said heavy snow eases drought slightly in western Minnesota, and it was basically saying that the snow that we've gotten won't take effect until the ground thaws. It won't go into the ground But this week's updated U.S. drought monitor showed subtle improvements in hydrological drought for heavy snow in western Minnesota from between Alexandria to Fargo. So it improved one category in drought designation due to recent snows. And it was talking about how the snowpack had liquid water in it, and that would have a positive effect on it. But then what struck me as interesting was they were talking about if we get more precipitate or more snow, it could be at risk for having a hydraulic flood on top of an agricultural drought. So that was interesting to me to have both of those at the same time. And so that's what I'd like to know more.
Okay. So kind of one important point that is bringing out there is, well, two things. First is when we think about precipitation, we tend to think about rain. We also have to think about snow and what snow is providing to us. The second is that the timing of that precipitation is very important. We can get, if we get a nice good spring rain, that's great, except if the ground is still frozen, because it's not going to go into the ground when the ground is frozen. Somebody else want to volunteer an article that they...
Did anybody...
Could we close the doors?
Did anybody else get to see Paul Douglas? Or was I the only one foolish enough to go out that night? Okay, I thought I didn't see anybody there. So yes, thanks to snow tires. What I'm going to recommend is that you go to his blog. You can Google, I always want to say somebody else, but anyway, Paul Douglas. And fascinating man. Not only is he a Republican, but he's conservative. And he's talking about weather change, and he had a couple of those little hot button kind of things. For example, he was saying anytime you have something such as climate change, it goes through 3 stages. I love this. Ridiculed, violently opposed, and third, accepted as self-evident. Do you love this? All right, so he had, I think the thing that most stuck in my mind, because he was also saying you have weather and then you have climate change. And climate change is the History Channel and weather is CNN. And with the warming of the Arctic, it is causing the jet stream to freeze, to stall. So that is one reason we are having rain. Oh, when's it going to go away? And oh, whoops, now it's drought. So just fascinating subjects. And he is ongoing with his, he's, I think, started at least 9 businesses. I mean, the man's a whirling dervish. So just incredible amounts of information off of his blog. So I was just, and I would have printed it out, but I'm technically challenged, and I thought if I did that, I'd have this whole blog, and that would be the end of my thing. So I highly recommend, if you didn't, since nobody else got there, I am going to get a medal for going this much. Got it.
Dr. Mark Seeley's got some really great presentations and, as well. If you ever heard him speak, he's very dynamic and very passionate about that topic as well. As part of this presentation, I've got some information to present to you, and we'll talk a little bit about some of those observed change climate conditions. Whether or not that's climate change, we'll leave it up to you, but at least we'll talk about observable things in the data. One more, and then we'll move on.
Oh, sorry.
Yep.
Okay. Once again, hitting the drought. I moved from Oregon, and we got lots of rain, and then in the summer we had forest fires. And I come here, it's the land of the lakes, and then we have drought again. So I've never really looked into it. I was curious about this whole, having all this precipitation, this whole, where this drought's coming from, and picked up an article, I guess it was the numbers, this was April 18th of this year, obviously, and it said initially that the rates have improved from 2/3 of Minnesota still being in drought to, previously 98% to now 2/3. So what impact, what was the change there? Like, was it just the climate change, or, like, because that's a significant amount, and then the other also significant amount is the drought is fading. 20% of the state had been in extreme drought, and that's quite a bit, 20%. It's not just like areas that I thought were perhaps remote, to now none of Minnesota is in drought.
That's what.
That's what it's
50% was still drought.
extreme,
Right.
extreme drought. So what and why? Because I don't have any background on that, and it just kills me because we get lots of this precipitation statements in Oregon, and then we were driving by Hood, and there's forest fires. And it's like,
And again, it's, you know, timing of the precipitation is very important. And you can go, you know, between those extremes very easily. You can also get a whole bunch of precipitation and still be in a drought condition because you've got storage in the watershed, for example, in your aquifers and wetlands and lakes and things like that. You get a whole bunch of precipitation. The deficit is just so great that it's, you know, it's just starting to try to replenish that. So you may not see any effects on the surface. So it's just going straight to groundwater, trying to replenish that. So as we'll talk about when we get to that part of the presentation, what we're seeing is a lot of extremes going up and down and back and forth. So, well, let's just jump into Hydrology 101. And the new syllabus showed that there were 4 learning objectives. So out of this, we're going to have some real basic, understand the rainfall, runoff, and movement of water, how we describe it, how we calculate it, how we measure it. So a lot of it is just very technical terms, introducing you to a few concepts so that you can sound like you know what you're talking about. Because it works for me. Second learning objective is to understand what influences how water moves. And so you'll find out that, that a lot of hydrology deals with water moving from either from one state to another or from one place to another. By state, I mean not Minnesota to Wisconsin, but from water to a vapor or from water to a frozen form. Third major objective, how does water shape the land? And I think that we can all kind of think of some examples, and we'll talk about that and show you some. And then talk about how those precipitation patterns are changing, what kind of impact that may have on our water resources. Let's start out with what is hydrology? We're very simple. It's the science of the properties of water, what it is, distribution, where it is, and circulation, where it goes. So what it is, where it is, where it goes. Hydrology is a little bit different from hydraulics. Okay? Sometimes you'll hear about, we're going to do a hydrology and hydraulics study. We're going to talk about hydraulics of something. Hydraulics is how man makes it move. I'm going to put it in a pipe and make it move. I'm going to dig out a channel and run that water to the channel and make it move. That's hydraulics. And we're just talking about how water's moving around all by itself. That's hydrology. Okay? Why do we study hydrology? Because hydrology is how water shapes the land. And sometimes it does it so very spectacularly. You get something like the Grand Canyon, which is a combination of both water and wind erosion. So we've got something here that over geologic time has created this new shape of the land. Shapes the land right outside our back door. It's a good thing this guy's got a canoe by his house because the creek's coming for his house. This was the before picture before a stabilization project. But you can see that the stream is really literally 10 feet outside his door. And it didn't used to be there. So water is shaping the land. Water influences where we live. I don't know if you can tell from this photo here, but that's St. Anthony Falls before the Corps of Engineers got at it. Why is Minneapolis where it is? It's because it's on the Mississippi River at St. Anthony Falls. Why are all of our major cities port cities? Because we use water for transportation, either on the coasts or on our major water river systems. Water influences where we live. We need it, obviously, water for life, but we use it very specifically for transportation. We use it for industry. We use it for recreation. We want to live by water. We study hydrology because flowing water picks up all kinds of stuff and it moves it around. The water is moving around as it's flowing over pavement, over a parking lot, over an agricultural field, through a forest. Anywhere water is moving, it's picking up and it's carrying stuff with it. And some of that stuff is big stuff, like trash. Some of it's little stuff, like particles of sediment. And some of it, if you've got really slow-moving water, is actually nutrients like phosphorus that actually release from the particles of soil and then dissolve up into the water itself. So we study water because it conveys stuff. Almost all of that stuff we don't like. We call them pollutants.
We call them what?
Pollutants. And we study hydrology because it's the only water we'll ever have. All of the water that ever will be is already on our planet. We're not making any more water. We're also not losing water. It's just going different places. When here in the upper Midwest, especially here in Minnesota, all of the water we have either comes up out of the ground or it falls from the sky. It doesn't come from anywhere else. It either comes from the ground or out of the sky. We're not on the downstream end of a big river like the Mississippi River. We're on the upstream end of the Mississippi River. We're sending our water somewhere else. So the only water we have is what falls out of the sky or what we can take out of the ground. It's the only water that we'll ever have. Okay, think back, some of us even further back, to middle school. If you remember the hydrologic, I was from the hydrologic cycle. Okay. Remember we talked about where water is. Okay, so where is water in the hydrologic cycle here? Where's the sources of water? Because on my clicker I had my laser pointer too. Okay, so where's the water here? It's in the ocean. Where else is it? Lakes. It's in the rivers. Okay, so we got wet water sitting out there on the surface, right? We have vaporous water up in the clouds. Okay, and we've got what kind of water underground? Groundwater. So we've got three places where that water is. It's on the surface, in the air, underground. Now, circulation of water. What are the processes that's circulating water here? Evaporation. So evaporation is moving, it's converting water from its surface water liquid state into vapor off of surfaces. Okay, so that surface might be off the surface of water. It might be off the surface of impervious surface, like a parking lot or a roof. It might be off the surfaces of plants, like corn or the leaves of trees. Okay, so it's water that is coming off of surfaces. There's another way water vapor gets up into the air. Does anybody know what that is, or want to hazard a guess? Or can you read that really tiny type from right back there? Transpiration. Transpiration. Transpiration is plants breathing, essentially. Plants take up water from the soil. They use that in photosynthesis, and then they release vaporous water from their stomata up into the air.
And a lot of it.
And a lot of it. If you ever go into like a wetland in July, it's like being in a sauna. Cattails are enormous transpirators. And you can just walk in there and just feel the water just coming off of them up into the air. Same thing in a cornfield. Corn is very similar to cattails. What's called its crop coefficient, which is just the rate that it uses water. We, as hydrologists, like to lump those two forms of conversion of liquid water to vaporous water into something called evapotranspiration. Yeah. And I'll give you an acronym for that, because you don't have to write it down all the time. It's ET. It's evapotranspiration. ET. Oh, your first acronym. So proud. Oh, we love our acronyms in water. We can construct whole paragraphs in acronyms. And I have.
So the two things you've talked about so far are evaporation and transpiration.
Right.
all that other stuff.
We haven't talked about jars, okay? So this is ET, water evaporating from the surface or out of the plants up into the air, into clouds.
So go through each one of those arrows. I can't read what that says. Are each of those arrows what you just talked about?
This just says transpiration from this crop growing here, evaporation from the ocean, evaporation from the soil, evaporation from the streams, evaporation from vegetation. Once it's up in the air, it forms clouds. And from the clouds come precipitation. Rain, sleet, snow. What else have we got in the last week? Snow. Evapotranspiration, precipitation. The last process is getting the liquid water from the surface down into the ground. And there are two terms that we use for this. The first one is infiltration. Infiltration is water that just soaks into the ground. So I'm going to infiltrate some water through my rain garden into the ground. Sometimes that infiltrated water goes so far down, it goes way down into the bedrock aquifers. We call that percolation. So infiltration is kind of at the surface. Percolation goes way down into the deep aquifer.
Could you define infiltration one more time?
Infiltration is water soaking into the ground. And we'll talk about how exactly that happens and how we measure it. So here we've got hydrology kind of in a nutshell. Okay, we've got water, we've located where it is, and we've located the processes that are going on. Just for fun information, there's another way that water gets from the air to surface water. That's not on this. You don't need to write it down. It's not going to be on the test. It happens in rainforests, but it also happens in a certain kind of forest, which are called montane forests. Those are forests that are up at high elevations, and those elevations are so high that they actually are in an area that maybe have clouds forming or fog forming. And those montane forests, when those fogs roll in, those fogs condense water onto the leaves of the trees, and then that runs down, and then it becomes runoff and surface water runoff. In some areas, that type of condensation can provide more water on the ground than just precipitation. That's a really significant factor. In some developing countries where they have montane forests, where those montane forests get logged and get removed, a couple things happen. First of all, you've removed that cover from the land, so you start to have erosion. The second is you don't have those trees there anymore to grab the water out of the air, and you start reducing the amount of runoff that goes downstream. And in one particular case study that I read, there was I think it was in Central Africa somewhere, where downstream they relied on a particular river. They were fisher people. They relied on the river, and that had plenty of hydrology to support a fish community that they could sustain their families on. They removed those montane forests, that water dried up, the river dried up. And so it had this unintended consequence of having these down in the valley kind of impacts on how they could live their life. There's one last process here that we're going to spend a lot of time talking about. In fact, almost this whole course or program is almost all entirely about. And that is this arrow right here. Water falling on the ground, then not going down into the ground, but going across the ground. And that is called runoff. Okay? So anything that doesn't go in the ground but goes across the ground
is called runoff. Does this ring a bell from you? Remember this from middle school? Any other questions on this? It's really important that you understand all the different parts of the hydrologic cycle.
Did you define percolation one more time?
Percolation is water that soaks into the ground and then goes down into the deep groundwater aquifers. Deep bedrock or groundwater aquifers.
And then runoff one more time?
Water that moves across the land. There's one more thing that's not on here that, as a stream ecologist, I'm really very mindful of. It's very important to me. Aside from out of the clouds, where does the water in streams and lakes and wetlands come from?
A lot of it just comes from seeps and springs off the edge.
So a lot of the water that's in lakes and streams and wetlands comes from the ground. When this water goes down, infiltrates or percolates down into the ground, it doesn't just stay there. It's moving. There's a very subtle movement, usually towards the nearest water body. So as this water gets expressed out into this water body through seeps or springs or just, moving from the soil into the water body, that's what sustains those water bodies. Why is White Bear Lake drying up?
Sprinkling watering grass.
Well,
and a whole lot of other things.
But it's drying up because we're pumping so much water out of the groundwater so that we can irrigate and sprinkle our grass. But because there's also population growth and people, want water, whether it's for drinking water or for industrial processes or other reasons, we're taking so much out of the groundwater that the level is so low that there's nothing moving sideways into White Bear Lake. Okay? Have you ever tried to canoe on Minnehaha Creek in, say, August? I did. Okay? So why is there no water in Minnehaha Creek in August?
They closed the dam at the
They closed the dam, right? But, it's a stream. Shouldn't there be water in it?
No, we were told some parts of it absorb the water. That's why.
So the water in this stream right here is being, it's called the base flow, is being supported by groundwater, which is moving laterally into it. Okay? So that groundwater moving laterally into it supports what's called a base flow. That's just flow that's in the stream, regardless of whether or not the dam's open, regardless of whether or not it's rained. There's just some base flow in the stream coming from groundwater. If there's no water in the stream in the middle of August, what's wrong? What's missing? There's no groundwater. Okay? We're going to talk about why there's no groundwater. Okay? We've done things that have reduced the ability of groundwater to sustain our lakes, wetlands, and streams, rivers, all those good kinds of things. So remember, when water goes in the ground, it doesn't just stay there. It moves. I think that's all I want to say about that. Okay. We're going to cover 4 basic topics on Hydrology 101. We're going to do 1 and 2, what is a watershed and how do we measure water. Then we're going to take a test and a short break because your head will be spinning. And then we'll get back together again and we're going to talk about what influences how water moves and how does it impact the land. We're going to take another little short break so you can write a paragraph for me. And then we're going to talk a little bit about precipitation. Is precipitation changing? What have we observed? And then you're going to get a final question to answer to take home. So let's just jump in. What's a watershed? Can anybody tell me the definition of a watershed? Go ahead.
The region into or from which the water flows into a body of water, whether it's a lake, stream, River, and that size can change if you're talking about like Minnehaha Creek versus the Mississippi River.
Great answer.
Am I close?
An area of land that drains to a water resource. Sometimes you'll see kind of a generic watershed depicted in a leaf diagram like this. I've never seen a stream that looks like that, or a watershed that looks like that. But this is just depicting, here's an area, it's got channels, that's a way for water to move down to a particular point. This point might be the Mississippi River, it might be a lake, it might be a wetland, it might be something else, but it's just draining to one particular point. This could be as small as your neighborhood. It could be as big as the upper Mississippi River Basin. So if you think about it, the Gulf of Mexico watershed is pretty much half the United States. Okay. We call other things sheds too. Go ahead.
I've also heard it described as a bowl. So if someone's not getting it, you could say, okay, any rain that falls in the bowl will flow to the center of the bowl. That helps me think about it.
Yeah. I think that helps. The only concern I'd have about that is that it's a really misshapen bowl.
Yeah. Okay.
It's because the outlets kind of over at one side. But, so we call other things sheds too. An area of, because it's just a handy way to describe things. We talk about lake sheds. Just an area that goes to a particular lake. Pond sheds. I've done stream sheds. The shed is just kind of a handy way of describing an area going somewhere.
An area that's the end or the location?
An area is everything in this whole area. A drop of water falls anywhere in this area will end up in the Gulf of Mexico. Okay? And then we show it, maybe give it in kind of more terms that might be easier to think about. This is the Minnehaha Creek watershed. Okay? Got 27 cities and a couple of townships. I don't see cities and townships. I see subwatersheds. Okay? Minnehaha Creek has got 11 subwatersheds. They're all organized around particular resources. So, for example, up here we have the Gleason Lake subwatershed. So everything in that area eventually gets down to Gleason Lake and out Gleason Lake Creek down to eventually to Wayzata Bay. Everything up in this area right here ends up going down Painter Creek down to Jennings Bay. The lower watershed is considered the Minnehaha Creek subwatershed because everything eventually makes its way to Minnehaha Creek and then out to the Mississippi River.
So north of Brownie Lake, Cedar Lake, where's the cutoff? It almost looks like it goes back.
It's right about.
Is it 55?
It's right around 394.
Oh, what's the line up above that?
It's 55.
But so it's not 55.
No, this is 394. Right.
Okay, so I
And
thought
right
that
up-
line was saying that
Yeah.
was the mark of the watershed.
Nope.
It's just the color.
It's the color,
Okay.
right.
So,
So
like
anything
394 or the
north of here
railroad track
goes to
down?
Bassett Creek.
Where?
Goes to Bassett Creek. So kind of over on this side, if you're over on this side, up here in Medina, you're going to Elm Creek. If you're over here in this part of Medina, you're probably going to either Riley Creek or to 9 Mile Creek.
So 9 Mile Creek goes into Minnehaha?
Nope. No. Well, the only thing that goes into Minnehaha is this area that's shown
Oh,
in
okay.
different
I thought
colors.
you were saying right. Never mind.
No, if you're down here,
out of the area.
right.
Okay.
So you can be across the street from this watershed boundary and not go to the same place.
So we can measure it that well?
Yep. You can go out and watch it.
How do they determine those boundaries?
You do it, a lot of what you do is by topography. So you're looking for a drainage break. So it can be as simple as looking at a street. Sometimes you can stand down at the end of a block and look, and you can see the block kind of goes up to a rise and then back down again. And right at that rise is where the drainage break is on your street. So half will go one way, half will go the other way.
So a divide. The
It's a
Great
divide.
Divide is a major
Right.
break between the watersheds.
And it doesn't have to be very big. You know, it doesn't have to be a ridge line. You know, top of a hill or something like that.
Now, is the one in western Minnesota, I forget the lake, does it actually flow out both ends, the Red River in the Minnesota? I forget what lake that is. Somebody said that once, that it goes two different
It's
directions.
likely, it could be, yeah.
One to the Hudson Bay and the other
Yeah.
to Mississippi.
It could. There are also areas that, depending on whether you're getting a little bit of rain or a lot of rain, if you get a little bit of rain, it might go one way. If you're getting a lot of rain, it'll go the other way. So that's what makes life as a hydrologist really interesting.
What is the difference between the area enclosed by the dotted line as opposed to the shaded area?
The area enclosed by the dotted line is the Minnehaha Creek watershed. That's its legal boundary. Okay? So each one of these shaded areas is its own sub-watershed. So down here you've got this purple area right here are the areas that go to Lake Minnewaska and Lake Virginia. We've got another one over here, this little one over here, tiny little watershed surrounding Christmas Lake. So that's the area that goes into Christmas Lake.
So watersheds can be as big as half the continent, and then they get smaller and smaller, and they're nested within each other.
We can get even smaller.
So the parts that are inside the dotted line but aren't shaded don't really drain to the Minnehaha Creek?
Are you talking about kind of these little spots right here?
Yeah.
That's there because there's a disconnect between the legal boundary and the hydrologic boundary. So they actually go somewhere else, but they're within the legal boundary.
Can we get a copy of that?
We'll put the whole PowerPoint presentation up on the website for you early next week. Yep. And the watershed district has all of these maps available.
No, if we focus even closer in, at a certain point we're so small of the area that we're thinking about that it doesn't make any sense anymore to be calling something like a sub watershed. So I like to use the word catchment as being the smallest area that I'm dealing with. So what I've done is focused in on the area just to the south of Lake Harriet. This is the Pamela Park area, and here's the creek and Meadowbrook up there. And you can see all those little blobs. Those are all little individual catchment areas. You can see some of them.
Point out what you're talking about,
Okay.
individual.
So here's a little individual blob right here. Okay, so here's an individual area that's all flowing probably to a single stormwater pipe, which is exiting this at a certain, or actually exiting going that way. Here's a whole area that's going north along this channel. Some of these are very big, and they're, 20 square blocks. Some of them are very small.
But all of those black lines outline what you're calling it.
Those are all catchments.
What about the two of them that have, or three that have the cross lines?
Oh, good catch. Those three there that have little cross hatches on them, those are what are called landlocked catchments. Those catchments do not have an outlet. Sometimes what they'll have is an outlet that only functions when you get really big rain events. So there might be a place, there might be an outlet, but there's a berm there, and it can only go up and over the berm if there's a lot of water. But that berm is keeping the water in during the smaller events.
Which ones are those?
So here we've got one right here.
Is that 50?
This is Pamela. This must be France Avenue right
Okay,
here.
France, okay.
Yeah.
Yeah.
And 50th
I
is.
see them now.
Yeah. Okay. Then kind of one over here and one up there. And it might be that particular area just drains to, sometimes like there's just a wetland in there, that the area just kind of runs to that wetland and it just stays there in that wetland. There's any number of reasons why it might be a landlocked catchment.
Sorry, can you please redefine or go over the catchment definition, please?
Catchment is a general term. I use it to mean the smallest area that I'm interested in understanding the hydrology of. So, we started out with the Minnehaha Creek watershed, and then we went to the Minnehaha Creek sub-watershed. Then we're kind of in the Lake Harriet sub-watershed. And now we're kind of going down finer and finer and finer till all we're interested in is these couple of square blocks right in here. Okay?
So it's an area of land.
It's an area of land just like a watershed. And actually, to make it even more confusing, in Europe they use catchment instead of watershed. So it means just the opposite of how we're using it here. And you can kind of see here that this particular figure has got little red arrows showing the way that the water flows. We look at this type of level of detail when we're constructing a model. We're trying to calculate how much water is running off the land. We want to model that. And we need to get down to really fine detail and really treat each one of those areas separately, individually.
So if someone wants to put a rain garden on their yard, do you do this kind of analysis at that level?
Not at that level, but it's the same concept. It's the same concept. We're looking at all of the area that would drain to that particular rain garden. And that might be their entire lot, or the catchment might be their front yard and their roof.
But you will be looking at aerial photographs of parcel level when we start to think about it.
So the concept here is that we're looking at a drainage area. That drainage area might be really, really small. It might be your front yard. It might be the 5 houses on your block that run to that catch basin down there in the end of the block. Or it might be several square blocks, or it might be 170 square miles. So, we've got this area that is running off water. How do we measure that? You could go sit in the stream like my colleague Joe here, and you can measure it. Those are the good days. You don't have to sit behind the computer. First thing you need to do is you need to measure precipitation. Okay? So to measure rain, we do it in a bunch of different ways. We're only interested in what we got, the rain that we got on our own property. You might be able to get by with just a little backyard rain gauge stuck in a really cute turtle, which when I went back to the website, they didn't offer it anymore.
But you have to bring it in winter to glass bridge.
And in winter, you're measuring snow, not rain, right?
It doesn't work.
There are other kind of more advanced versions of those, different types of rain gauges. The most common one that you'll see, and if you start looking around for them now, you may notice them, are what are called tipping buckets. Right outside the Minnehaha Creek offices, if you've been there, you've seen kind of a weather station that kind of looks like that. Okay. In that weather station, you got something like this. Basically, this gold part here is a funnel. Rain falls in it, goes down this funnel. Down at the bottom, there's a pivot. Okay, so we've got a what's called, even though it's triangular shape, they're called buckets. Okay? So you've got these 2 buckets that are sitting on that pivot. And as the water runs down, it goes into one bucket. Once that bucket gets filled up, it tips over, and it drains out, and this bucket starts filling up. Once it fills up, it tips over, it drains out, the other one starts filling up. Every time it does that, there's a magnet on the end of this, and there's a little switch right here. Every time that it tips, it activates that switch. And then there's a little electronic signal that comes out into this device right here. Every week or so, you can go there and download the data, and it tells you every time that bucket tipped and what time it was. Each one of these buckets are calibrated so they hold an amount of water that is equivalent to a certain depth of rain. So depending on the size of the rain gauge, it might be that this bucket is sized to hold 0.1 inch of rain. So you know that every time that tips over, you've gotten 0.1 inch of rain. So all you got to do is count how many times it tipped over. And so you know how much rain you've got.
So this has to be hooked up to something electric?
Yeah, it's, you know, they plug in. When you've got a device like this, you just plug it into your laptop and you upload the data.
It keeps the data until you plug it in?
Yep. Now, NOAA, National Oceanic, has a network of larger rain gauges like that. They actually use telemetry, where instead of having to go to there and upload the data, it will, over radio signals, send that data. So we can measure the rain that fell in your backyard. We can measure the rain that fell in an area. We can measure the rain that fell over a region. You'll get access to this presentation. If you've never been to the State Climatology Office website, go. You'll have a great time. There's so much data there, so much interesting information about current and historical data of precipitation, temperature trends, what's happening with climate research. We've got Mark Seeley's blog is there, just lots of stuff. This is something that I just pulled out over there. It's really busy, so you may not be able to really see what I'm trying to show with it. All this is showing is this is kind of the western metro area. And I don't know if you can see, but there's lots of orange dots kind of scattered all over the metro area here. Each one of those are people that maintain a backyard or front yard weather station. Okay? So you can see that they're scattered all over the metro area. You can go on the State Climatology Office website and go to the Hamel, if you're interested in what's going on around Hamel, and pull up the Hamel data.
So are those like that NOAA one, or are they like that?
They're like the tipping bucket one. Okay? So these are people and a lot of these people have been maintaining these for decades. So we've got a really nice long-term record. And some of them are fairly new. One of these is the one that's in Wank's back parking lot.
What did you say, Wank's?
My company, Wank Associates. So we have one in our back parking lot. And again, this information then gets aggregated. The State Climatology Office uses this information, compiles it, and uses it when they're analyzing what's happening with the trends in weather in the state of Minnesota.
Can anyone just say they want one of those?
Yeah, I mean, you can buy them. They're a couple $100.
But I mean, like, is it not very stringent? Like, I could say, I want to be one of those weather people.
Yeah, I mean, they will send you through training. And you'll have to commit to doing it.
Okay.
Yeah.
Probably wouldn't want 5 people on the same
Right,
one.
and they'll look at your site and see if it's really a suitable site.
Okay.
Because sometimes it can be influenced by what's around it.
Well, that's kind of what I was wondering, is the accuracy part of it.
Yeah.
So that makes sense.
NOAA maintains 144 climate reference network sites across the United States. So the Climatology Office is interested in what's happening in Minnesota. NOAA is interested in what's happening across the United States. So there's 144 installations like this scattered across the United States. And these are big-time weather stations that, again, use telemetry to report their data back to NOAA. I don't know which one of their offices collects it, but again, all that information that is available on websites, so you can pull that up at any time if you're interested in seeing what the big picture is going on. We're also interested in measuring snow. I'm sorry, did you have a question?
How does the U.S. Geological Survey tie into the NOAA data? I was on the website today. It looks like they have a bunch of information, hydrological.
USGS maintains a network of monitoring stations. And with their monitoring stations, they often have a weather station. So they may have a gauge on a river and then have a weather station right there so that they can keep a record of flow in the river and then also understand what the precipitation is right there at that gauge. So a lot of those USGS stations are on that orange network.
Okay. So they communicate.
Yeah. So they're all reporting the data up to the same collection place. This is me sneaking out.
Yeah. And you're on film.
Is this
Wave to the camera.
I'm sorry. As far as the question of how we measure water, was it just measuring precipitation? Was that just the answer to that question?
We measure the amount of rain that we get.
So it was actually that diagram that you showed us.
Mhm.
Okay.
So we also measure the amount of snow that we get, because we were asking questions earlier about how do we all of a sudden go from being in extreme drought to not quite so droughty. This is a network of snow monitoring stations that the National Resources Conservation Service maintains. I don't know why it's not NOAA, but NRCS does. And you can see each one of those dots is a snow monitoring station. It's part of, I love this, the SNOTEL network. I'm not really sure why it's so dense in the Rocky Mountain area, but we've got one in Wisconsin and 2 in Minnesota. And it may be because we're collecting data adequate enough for their needs. But one of the reasons why there's a very dense network in the mountains is obviously they get a lot of snow, and when that snow melts, it's transporting a gigantic amount of water. So there's a lot of need to understand what the snowpack is, what the water equivalent of the snow is, and when that starts to melt, how much volume is headed downstream to the reservoirs, so that all those reservoirs out west can be managed, and they know how much water to expect. So there's a lot of really intensive monitoring of snowpack out west. So if you would go to this website and click on one of these dots, it would bring up a photo of that monitoring site, and it's literally a big pad on the ground, and then surrounded by a fence, and then with some telemetry. And then that pad actually is heated. So when snow falls on it, it will heat, and then it will that melted water will run off, and then they can measure the volume of that water that's run off and say, okay, that 12 inches of snow generated 1 inch of water.
Why are they measuring it in the south? I mean, am I misreading? Like I see all.
Oh yeah, why is there a SNOTEL site in Houston, Texas?
I mean, there's a lot of
Florida. There's a lot of
Yeah, there's this really odd little concentration down here in Louisiana and Arkansas. And
it's such a rare event, they don't want to miss it.
Maybe. I don't know. I don't know the answer to that. I don't know why there's a big blob in Louisiana and one in Wisconsin.
We'll do the different colors and different things.
The different colors, up on top, I don't know if you can read that, it says snow water equivalent as percent of normal. So normal snow water equivalent is 12 inches of snow equals 1 inch of water. So that would be their 100%. So that they're calling this kind of dark green. So if your dot there is a dark green, it means you've got snow where if you've got 12 inches of it, you've got 1 inch of wet water.
What's the gray one?
Missing.
What does that mean?
It means that there's no snow on the ground.
So we have a station with no snow.
So on this particular day, this snapshot in time, all these stations that are gray don't have snow on the ground. And where it's a color, it means that they have snow on the ground. And if you're purple, you're 140% of normal. It means you got really, really, really wet snow. Kind of like what we got, was it last week or whatever. So we're out there, we're measuring snow. We're measuring snowpack up in the mountains. We're measuring snow locally because we want to also know how much water that we're going to get out of that snow and what that's going to contribute to our waters. Okay, this is one of the hard words that you're going to get today. It's really not that hard. I'll let you write this down. And actually, I've got a series of graphs. They're all going to have the same title on them, so while you're writing, I'm going to work your way through it. An event hyetograph, that's how you pronounce it, a hyetograph, shows the distribution of precipitation over time. So down along the x-axis here, these are hours. So you've got starting at 4 a.m. one day, and then you're getting later and later, and here's 1 p.m., and you're going to 8 p.m. and down to 2 a.m. here, so it's a little over 24 hours worth of data. So each one of those bars said for every 1 hour period, we went out to our tipping bucket, and our tipping bucket said that in that 1 hour period between 5 a.m. and 6 a.m., we got 0.05 inches of rain. And then in the next hour, we got another 0.05 inches of rain. And then maybe between this time, between 9 and 10 a.m., we didn't get any rain at all. And then around the afternoon, starting around 2 p.m., it started raining really hard. And in that hour, we got half an inch of rain over that hour. So it's just going through hour by hour, how much rain did we get. This is our hyetograph. It just shows the distribution of precipitation over time. We like to look at precipitation over periods of time. You can construct one of these hyedographs for 3 weeks. But we really like to, as hydrologists, we like to look at certain periods of time, one of which is 24 hours. How much precipitation did we get in 24 hours? So here we've taken this hyetograph and said, okay, for that 24-hour period between 6 a.m. one day and 6 a.m. the next day, we got a total of 3.85 inches of rain. So we just added up all those bars, and it added up to 3.85 inches of rain over 24 hours. But you can see that for part of that 24-hour event, it was raining really, really hard. So we would like to know, when it was raining the hardest, how much rain did we get? How intense did we get? So one of the periods of time that we like to look at is the 6-hour event. So in the 6 hours, which 6 hours did we get the most rain? So here we've got highlighted from 2 p.m. to 8 p.m. In 6 hours, we got 1.55 inches of rain. Now, sometimes we look at the 1 hour event, sometimes we look at the 12-hour event, sometimes we look at the 15-minute event. Mostly we look at the 24-hour event. But looking at the more frequent events helps us better understand how intense the rain was. Period, if so, what do we get? We do that because once we have our rain networks, or precipitation networks, where we've had all those gauges out there collecting data, sometimes for decades at a time, we can figure out whether that 3.85 inches we got in 24 hours was a lot, was it out of the ordinary, or was it just kind of average? So we're interested in some way to describe how frequently a particular rain event happens. We call that the return period. Okay? So the return period is calculated as 1 over the probability. So an event that has a 1% chance of occurring, we calculate as 1 over 0.01 equals 100. That's a 100-year event. Everybody thinks in terms of 100-year, it's more accurate to call it a 1% chance. Because we all know that we've gone and had periods of time where we've had a 100-year event year after year, or sometimes 2 or 3 of them in the same season. It's more accurate to call them probable. You can flip a coin and get 5 heads in a row. It's very improbable, but it can happen. You can get multiple 100-year events in the same year. An event that has a 50% chance of occurring, 1 over 0.5, is a 2-year return event. We're interested in the 100-year. Often we're interested in the 10-year. So given that, what's a 10-year event? What kind of probability is a 10-year event?
10%.
10%. An event that's got a 10% chance of occurring is a 10-year event. There's a very complicated way of calculating what those specific precipitation events are, which we won't go into here, but if you're really interested in it, I can do like a master class. Yes, ma'am.
So
when we have frequencies where you do have, say, 5 years in a row where you do have that 100-year rain event, when does that percent chance change to allow for those higher amounts?
That's a fair question, so I guess I'm going to have to delve into this topic just a little bit. Basically, when you're figuring out the return, the probability that something is going to happen. First of all, it helps if you have a lot of data over a long period of time. So it's in essence, it's just simply a math exercise. So if you think about it, let's say that I've recorded rain in my backyard weather station for 30 years. So I've got 30 times 365 points of data of how much rain happened in that 24-hour period. Some of them are zero, some of them are big numbers. Okay? So I've got all this data in my Excel spreadsheet, and I'm going to tell Excel to order that from highest to lowest. Okay? Then I'm going to do some mathematical things to it. And the equation that's going to pop out of that mathematical thing is going to allow me to say, out of all of this data, once I've graphed it and I've looked at how frequently things happen, there's a cluster of events right around the 10% probability. You know, out of those 1,000 events, they happened 10 times. No, 100 times. And that's this cluster around this amount of rain. Okay, so I can do some more math and say, oh, that's 2.5 inches. Okay. Then I've got only a couple of values over here that are really big events that have only happened a couple of times. So I know that happens very frequently, so out of my 1,000 times, maybe they happen twice. So that might be my 500-year event around there. It's more complicated than that, but that's basically what it is. So now you've got this long period of record. This is just actual data that you've collected over time. If you start having a whole bunch of really big rain events, okay, those really big rain events are going to show up more frequently in your data record. Okay, so that percent probability is going to start increasing because you're going to get more and more of them in your data record. So if you've start getting 100-year events every year, eventually the 100-year event is going to become, or that's going to become more like a 90-year event. Okay. So, and we'll talk a little bit about that because that's happened now. That's something that's being considered, which we're going to talk about after the break. Something which is called Atlas 14, where they've done just that and figured out that those probabilities have changed. So, return period, a 100-year event has a 1% chance of happening. 10-year event, 10%. 2-year event's got a 50% chance of occurring.
Excuse me. Does that assume within a given 365-day
yes.
year?
Yep. Within a given 365-day year, if you've got a 1% chance of that occurring in that 365 days, that's a 100-year event. Oh, I guess I talked about it before the break. Okay, so we're getting close to the break. Which rainfall events are we interested in? Okay, so over on the side there, I hope you can see it in the back. It's a little bit small. We've got return frequency. The first row is the 2-year return frequency. The second is the 10-year. Last one is the 100-year. Turn that into probability. The 2-year return frequency has what percent probability? 50. 10-year, 10%. 100-year, 1%. Okay. Now, I told you before that we like to look at different periods of time. We like to look at 24 hours, but we also might be interested in all these other types of events. So we've got 24-hour, 12-hour, 6-hour, 3-hour, 2-hour, 1 hour, 30 minutes, 15 minutes. If you can read the citation on the bottom there, it says U.S. Department of Commerce, Weather Bureau, technical paper number 40, also known as TP40. In that technical paper, the Weather Bureau looked at a long period of record of data down to the 15-minute mark. So the little tipping bucket, they weren't just recording what we were getting by every hour, they were recording by what we were getting every 15 minutes.
and went through that probability analysis and said there is in the Minneapolis metropolitan area a 24-hour, 2-year return frequency event is a rain event of 2.8 inches. The 100-year is 5.9 inches. Okay? You can see that those values are a little bit different for each one of those rainfall events. And generally, what's happening as you're moving from left to right is the rainfall intensity is increasing. So that's why you're looking at that those really fine events. So to get almost an inch of rain in 15 minutes is a lot of rain. Okay. Technical paper number 40, TP40, came out in 1961. The period of record extended back to the Dust Bowl years. We've been collecting a lot of precipitation data since that time. We've now got a really long period of record. TP40 is going to be replaced this year by something called Atlas 14. I don't know why it's called Atlas 14. That's what it's called. So Minnesota, actually the whole upper Midwest, will be published in 2013. It's based on a longer period of record. It's more accurate. Those values are different, especially for the 100-year event. Those values are not different because of climate change. Those values are different because we have more data. We've just got, we've got better models, we've got more data. So how different is it? Okay, the 2-year event, that 2.8 inches doesn't change very much. The 100-year event will be going up 32%. That 5.9 inches will now be 7.9 inches.
Cool.
It doesn't mean that we're getting more bigger storms. It means that we didn't have enough data to really understand that there were a lot more big storms out there than we realized. So when we say we seem to be getting these 100-year events more frequently, it's because we defined our 100-year event wrong before. We based it on an old period of record that included the Dust Bowl, and we've got 50 more years of data now to work with. What that means is that for those of us that design things for a living, we design things based on certain amounts of rainfall. So if I'm going to design a storm sewer pipe that's going in a new development, oftentimes we're using the 10-year rain event. We're assuming that storm sewer has got to be sized to convey the rainfall that we get in a 10% chance rain. Well, under Atlas 14, that's actually going to be 14% more rain than what we thought that it would get. So that means that the storm sewer that somebody designed last year under TP40 is probably undersized. Okay.
Do you know if this new one going in around Calhoun area is based on the old then? They're tearing up all these streets this summer?
It's probably based on the old. Now, on the plus side of that is that a 10-year event is a pretty generous rain event to be designing stormwater infrastructure under. Back in the old days, in my neighborhood up in Camden, we've got 2-year storm sewers. So that means that if we get anything more than a couple of inches of rain, our storm sewers are all surcharging and the water's coming out of the catch basins and stuff. So a 10-year event is pretty generous. So even if you're really, it's really an 8-year, whatever probability that is, that still gives you a lot of leeway. So we haven't noticed any real, significant flooding in some of those areas that are, that have been designed recently. So we think that we're building in a pretty good amount of margin of safety. But we're going to have to start using the new numbers when it's official. Yes.
How many 100-year events have we had recently, say, in 20 years? I remember 87, was it?
Yeah. You know, when I was pulling information together, I know that Mark Siggy had some graphs in it, and I don't remember now what it was, but it was showing the frequency of rainfall events and how those have changed. And we'll talk a little bit about that later. But yeah, I mean, we've gotten more big storms, and part of that is, that there are some things changing. All right, we're winding down to this part of the presentation. We're almost there. Other events of interest, from your perspective, if you're going to be out there designing a rain garden or infiltration basins or helping people put in rain barrels or deciding how many rain barrels they're going to need for their particular property, you're interested in the one-year event. You don't care about those probabilities. I'm sorry, the 1 inch event. You don't care about those probabilities. Just think about 1 inch. It also makes it really easy to calculate. There's another event size out there that you might come across, and that's called the water quality event. And that's somewhere around 1 1/4 inches to 1 1/3 inches. The reason why it's called the water quality event is if you squint real hard at this graph right here, there is a gentleman named Dr. Robert Pitt who has done a lot of, and then Roger Bannerman, who've done a lot of research in Wisconsin. They did some really intensive monitoring in the city of Milwaukee. And the water quality event, which is this red line right here, conveys about 90%. This is pollutants. Conveys about 90% of the annual pollutant load. So the 1 inch event is about 70%. So that's why we say 1 inch is a nice round number. It's a good one to work with. You're still getting at about 70% of the annual pollutant load. Let's just keep it simple and deal with just 1 inch. You might see that water quality event around.
So 1 inch was 70?
It's about 70% of the annual.
And what was 1.25?
It's about 90%.
90.
And we're saying 70% of the pollutant load.
Yep. On an annual basis, about 70% of it.
And can you define pollutant load?
Well, yes, I will define it, and then you'll talk a lot more about it at your next class.
Okay.
Pollutant load is, remember when water runs over the surface, it's picking up stuff?
Mm-hmm.
Okay. It's picking up pollutants. So a pollutant load is just the mass of that pollutant that it picks up. So I'm going to be down there at intercepting the water before it goes down to the catch basin. I'm going to let it run into my pail. And I've got a liter of water, and I'm going to go in this liter of water, and I'm going to measure how much sediment is in there. So that sediment then will be expressed in terms of an amount, like a micrograms per liter of water. That's your load. So it's just the mass of a pollutant that's being conveyed by water.
So you have the 1 inch event.
Mm-hmm.
What's the time period?
Instantaneous. We call it, it's not instantaneous, but we call it instantaneous. We don't care how much time that it occurs over. It's just 1 inch of rain.
So we're going to be helping people decide based on whatever I'm supposed to call it, that roof mass or area with a 1 inch rain on it.
And it might fall in 15 minutes.
Okay.
It might fall in 6 hours. It doesn't matter. It's just 1 inch of rain.
But within a day, usually? Or I mean,
Yeah, because after that it's going to start evaporating and going away.
Right, okay, so I mean...
Yeah. We call it instantaneous. It's not really instant, but we call it instantaneous because we don't care how much time it occurs over.
So if you get 2 inches, it's only going to take care of 1 inch.
Yeah, right. 1 inch will run off. 1 inch will go into 1 inch will go into the rain garden, which you won't be able to take anymore. So the rest of it will run off. Right. All right. How do we calculate runoff? Runoff is really, really easy to calculate, especially when you're dealing with 1 inches. All right. It's area times rainfall depth. That equals your volume. So you're working with somebody, and here's their yard. Okay, we've got a 1,200 square foot footprint house, an 800 square foot driveway, and then they've got a lawn surrounding it. Okay? So what you want to do is you want to help them put in a rain garden to deal with the runoff from their house and their driveway. Okay? Your impervious area, the hard surface, which is the roof of the house and the driveway, 1,200 square feet plus 800 square feet is 2,000 square feet. We're going to multiply it times the rainfall that we're interested in, and that's 1 inch. To convert that 1 inch to feet, we're going to convert it by saying 1 foot is equal to 12 inches. Remember doing that unit analysis back in high school?
No.
Okay. 2,000 times 1 divided by 12. Okay.
Is
So
that 1 foot over 12 inches? Or
1
is
foot
that
over 12
thing
inches.
over 12?
Pardon me? Yep.
Ultimately, it doesn't matter.
Yeah,
Okay.
it's just the conversion.
Yeah, 1 foot is
Oh, okay.
12
In the other.
So when you're doing your units then, you're multiplying square feet
Yeah.
times feet,
Yeah.
and you're coming up with cubic feet, right? Because your inches are going to go away because you've converted it. So if you do the math, 2,000 times 1 divided by 12 gives you 166.67 cubic feet. Diane, you say, I'm not used to thinking in terms of cubic feet. How many, put that in some units I can understand. 1 cubic foot, which by the way is a cube, 1 foot on each side, right? 7.5 gallons of water. So 166.67 cubic feet is 1,250 gallons. If that helps you put it into perspective. Right, so sometimes your rain barrel is sized in terms of gallons, so you need to know how to do this in terms of gallons. Sometimes if you're sending this to a rain garden, you're going to be working in cubic feet, so you need to know how to do it both ways. Area times rainfall depth times a conversion factor there to change your inches to feet gives you cubic feet. Multiply that times 7.5, that gives you gallons. In case you wanted to know, even though I told you you only care about 1 inch, our 5.9 inch old 100-year event would run off over 7,000 gallons. So unless you're lining up a whole bunch of rain barrels or just around the perimeter of the house, most of it's going to run off.
Wait, what?
Oh,
Won't a lot of that water absorb into the ground?
we're going to assume that that's all going out off the impervious surface towards your place that you're interested in directing it to, whether it's a rain garden or a rain barrel. In practice, you know, this part of the roof might go to a downspout over here, which just runs out onto the ground here, which then might just soak into the ground. You know, this half of the roof might just go out to the backyard. So this is a really simple way of showing how to do it. When you get to that little further stage, I can't remember which lesson it is, where you're actually figuring out how to size the rain garden. One of the things that you'll be looking at is, all right, where's all the water going on this site? So that I know, okay, this might be a 1,200 square foot footprint house, but I only need to deal with half of it because the back roof is going to the backyard. I only need to deal with the front part of it. So just for purposes of concept, you've got an area times the depth and goes above. Okay, before we take a break, or do you want to take the test after the break?
Let's do it now.
All right. Okay. Number 1 to 12 in your journal. Try to do it without looking at your notes.
What are we doing?
All you're doing is defining very briefly what each one of those terms mean. What is transpiration? Give me a couple words or a sentence. It doesn't need to be real detailed. Just generally, do you understand what that term means? If you can't see it, can you guys in the back see it?
Yeah.
Okay. Transpiration.
Plants,
Well, it's being used by the plants. It's not evaporating off the plants. It's being going from the plants. Infiltration. Water into the ground. Hyetograph. That's precipitation over time. Tipping bucket. Measuring rainfall. It's a fancy schmancy rain gauge. 100-year event.
1% probability.
0.01% probability. 1%.
So 1%, which is like 0.01.
But the probability is 0.01, right? And then
Yes,
1 over.
yes, but 0.01 is 1%.
Right.
Give yourself half credit. I do that for next time. Watershed. That drinks a water body. Hydrology. Study of water and its movement. Where it is, where it's going to. Cubic foot. Oh, good. I heard somebody say 7.5 gallons, and I heard somebody say a box. 1 foot on each side filled with water. Runoff.
Moves across land.
Okay, doesn't soak into the ground. Lake shed. Okay. Return period.
1 over
Okay, return period. 1 over the probability. Right. Okay. Base flow. There you go. Groundwater. Yes, groundwater because it wasn't on. There was one that I had to add to it. To the hydrograph.
I still don't understand what it is.
Hydrologic. Okay. Base flow is groundwater. Remember, groundwater isn't static. Groundwater is moving. So it's groundwater that moves into the stream, so that the stream always has a flow. It's called its base flow.
What was return period? When everyone talks at once, and I end up not.
The return period is just 1 over the probability.
Oh, okay. Thank you.
Okay. So hope you got most of those right.
So the real test will be once this gets posted, then you go back to it, and whenever it gets posted next week, to see whether you can still do it. Let's take a 10-minute break. All right, let's come back in here. We'll restart at 5 minutes to 8.
What happens? That's it. We're just going to have people together. Oh man, that
About 255 miles from Minneapolis. About an hour away from It's a section of college. And I still feel like that. If I could, out there just to be able to the cities and things.
And then you'll notice there's some missing from later.
But then, I'm a geeky scientist, hydrologist, ecologist kind of person, so what I think is why maybe different things. What influences how water moves? When we're talking about how water moves, we're talking about runoff. What influences that runoff? The first big one is soil type. Okay. On the right side is the USDA soil triangle. And soils are described in terms of what combination of sand, silt, and clay that they have in their mineral component. So if an individual soil will fall somewhere along that soil triangle, it'll kind of lean towards having more of one type of soil particle type. I think that the type of soil is important because if we look at the diagram on the right, you see on this side is a close-up of sand. Sand is composed of big irregular particles. Those irregular particles are kind of floating around with lots of spaces in between them. And those spaces in between them are called pore spaces, P-O-R-E, pore spaces. Just like the pores on your face, these are pores that are in the soil. So sand's got big pore spaces. In the middle is silt. Silt is composed of irregular particles too, but they're really small. So they're really small, but because they're irregular, they don't get packed in very tightly. So they've got lots of pore spaces too. It's just that their pore spaces are really small compared to the pore spaces of sand. Clay, on the other hand, is really small, very uniform types of particles that get packed in together really tight. Hardly any pore spaces at all. So you can see those particle diameters. Sand is anything more than 0.05 millimeters up to 2 millimeters. Big particles, irregular, lots of pore space. Clay, small particles, very uniform, not very much pore space at all. Why do we care? Because that soil texture, those, what that soil is comprised of, influences how much can be infiltrated. So if it can't infiltrate, it runs off. So on the left, you've got sand, you've got those big particles that are irregular with lots of big pore spaces. You can pour all kinds of water on it, and it'll soak it right up. If you go up on the Anoka Sand Plain, up in Blaine and north of there, that's all sand. They can't keep water in their stormwater ponds. The water just goes away. They got unlimited infiltration practically.
So it'd be safe to say that sand absorbs water?
It's not. Yeah, it's not really technically absorption, but that's what it's doing.
Or I guess like a sponge effect.
Yes, sand is kind of like a sponge. Silt, again, because it still has those irregular particles, they're just smaller, so they've got pore spaces, it's just smaller. It can take some infiltration, but at a certain point it gets filled up and it starts running off. Clay on the other side, you can see that this water doesn't penetrate very far at all, if you can see up here, because we've got these really tightly packed particles. Can't get in there, almost all of it will run off. Sand, it'll infiltrate right through, it's very absorbent. Clay, most of it will run right off. So, how much runoff you get and how much infiltration you can get depends very much on the texture of your soil. You'll explore that more when you're actually going through the hands-on design exercise. And why do we care about that? How do we classify those types of soils? Well, the Natural Resources Conservation Service, which used to be called the Soil Conservation Service, which was established right after the Dust Bowl when we figured out maybe we better keep track of our soil, has classified almost all the areas of the United States according to their soils. So all those soils are evaluated and typed, and one of the things that goes into typing those soils is determine what's called their hydrologic soil group. HSG, A through D. A soils are sand, loamy sand, those big particles, lots of big particles of mineral soil. So if somebody says, I got A soils, you can say, you'll infiltrate, no problem. Okay? B soils are the most common soils around here. Kind of a nice silty loam, you pick it up and it's kind of a nice dark soil, and you can kind of feel that there's some sand grains in it. That's kind of nice and brown. That's a silty loam. Those are B soils.
What does loam mean?
Loam is a soil which is comprised of both mineral and organic particles. It's kind of fluffy. So if you pick up some soil and it's, it feels kind of, you can break it apart and it's kind of nice and fluffy, that's a loam.
Mineral and what?
Organic.
Do all soils fit into one of those categories, or are there other types
There's
of soil types?
some kind of technical variations on them, but
they all fall within one of these 4 categories. Okay? Going from A down to D. D is basically your crappy clay soils. You've got D soils. You're going to have to work really, really hard to amend those soils to get anything to infiltrate, to get your rain garden to work. Okay? So when somebody says to you, oh, those are B soils, they're talking about their hydrologic soil group and its ability and capacity to infiltrate, to pass water through it. Going from A, which is the easiest, to D, which is the, sometimes you hear them called really tight soils, which you can't pass water through. So the state stormwater manual, oh, I'm sorry, before I get to that one, I'm going to show you this map, which is kind of the upper Minnehaha Creek area. Highway 12 down the middle, Highway 494, up and down here. So all those different colors there indicate different hydrologic soil groups. So those little patches that you see in red are A soils. They're very sandy. You can see there's not very many of them in that particular area. That kind of buff, kind of grayish, kind of what looks like background color are B soil. So you can see that most of that area is B soil. Areas where you see which a hatch mark are sandy clay C soils, and the green are really clay soils. A lot of times those are associated with wetlands or in the vicinity of a wetland.
The clay?
Clay, yeah.
That's counterintuitive to me.
Yeah.
So is it underneath the kind of muck that you're talking about?
Because it's muck that gets compressed and it becomes clay. And they will be in an area that maybe has been a drained wetland. So it'll get very mucky, which will become very clay-like. And in fact, I think that's that big wetland. Yes, it is that big wetland that's across from Wayzata. That big green splotch there. Now you see that there's some other colors there. There's some like purple vertical bars, and there's some blue horizontal bars, and some dots there. And I said before that there's some kind of technical variations on some of those. I won't go into a lot of detail, but I'll just say that those are soils that when they're dry, they act one way. When they're wet, they act another way. So these areas that are kind of in white dots are what we call A/D soils. So when they're dry, they infiltrate really well. But when they're wet, they don't infiltrate anything at all. So there's a particular property of that soil which makes it, and it might be a physical property, it might be the slope of the land that it's on. But there's some particular property of that soil which says that, yes, it's A soils, but it's only under certain conditions. Yes?
So when you say on the pretty much where the letters are A and B, is that pretty much a fusion of the elements? So to
Yeah,
say?
it's just depending on, it can act in different ways depending on soil moisture.
So if it's, I guess the top part, the snowy red, yellow, not red, yellow, the white dots up there, it would be, for example, sand plus silty clay loam.
Well, it's not really that it's a fusion, it's just that under certain conditions it'll infiltrate really well, and other conditions it won't infiltrate anything at all. And those conditions might vary depending on the particular location.
Could you give an example?
It's all different. Sometimes it's just where it is on the landscape. There's just something about that it's in a low spot, or it's a weird slope or something that says that, once it gets wet, it just can't infiltrate. So it's different for every location. If you look at in Minnehaha Creek, helpfully in the management plan, we have figures that show those hydrologic soil groups for the entire watershed, except for most of the city of Minneapolis. In the city of Minneapolis, unfortunately, when the soil survey came through, most of the city of Minneapolis had already been built up. So when the soil survey came through, all they did was say, it's just, I can't remember what they call it, it's something urban soils.
And if you don't know what it is, we don't care. So it just comes through as being unclassified. So that doesn't help you for design purposes, but that doesn't matter because you're going to be using an actual measured rate when you're designing something.
So the profile, does it go, do you have a depth or does it change over, like how far down do you go? Do you see any change?
You mean for those that have a dual classification?
Or even just the single, like well, I guess dual, yeah, but do you see a change in any?
Yeah, I mean, there is definitely a soil profile.
Profile, that's the word.
Yeah, it's soils are classified based on the top 3 horizons. So there's like what they call the O horizon, which is right at the very top of the soil. Then there's the A horizon, and then the next one is the B horizon, and those depths vary depending on the type of soil. So they will look at all those properties of all those layers and say, okay, this is this particular type of soil. This is how it's going to work.
And then whatever you're designing, that's on how deep you go. That's what you need to know.
Right. When you're designing, you're going to be ignoring this, basically.
Yeah.
but when you're designing,
for the test.
when you're designing, you're actually going to be measuring the amount of actual infiltration. Okay. You're going to be measuring it where you're going to be, for example, if it's a rain garden, where you're going to have the rain garden, and at the bottom. So if you're going to design a rain garden that's 18 inches deep, you're going to dig down 18 inches. And then you're going to dig farther down from that, and then you're going to measure the infiltration.
Type in our own soil, actually.
Right. Yeah. So, I show you this because it is so common for someone to say, oh, what kind of soils do you have? Oh, I got A soils. Yeah. So you need to know that lingo and what that means. The stormwater manual, in this really, really tiny type, which probably only in the front row can read, has helpfully classified the soil textures by soil group, and then come up with like an average infiltration rate for each one of those soil groups. So depending on exactly what kind of A soil you have, on average you might have an infiltration rate of 1.63 inches per hour, or you might have 0.8 inches per hour. Again, ignore it because you're going to be using actual. If you're somebody who's going to be doing hydrologic modeling and you're going to be building a model of a big watershed, you want to estimate how much runoff you're going to get, I want to know then that I've got B soils, and I'm going to assume that my infiltration rate is going to be 0.6 inches per hour. Because I'm not designing something. If I'm designing something in the ground, I want the actual. If I just want to estimate it, I'm going to use these.
Is there anything special about the GP and the GW?
Those are the soil classification abbreviation. So GW would be gravel well graded. So that's the only thing special about it. Sure. So you don't have to write out well graded gravel or well graded gravel with sand. You can just say it's a GW soil. Again, you don't care. Another thing which influences infiltration versus runoff is compaction, which makes some sense. On the left side, we have non-compacted soil. So we've got our particles in there, and we've got big spaces in between them. In our compacted soil, we've got small spaces in between them. Soils get compacted in a number of different ways. They can get compacted by construction vehicles driving over them. They can get compacted over time just from the sheer accumulative impact of pounding rains and people walking over them and walking over them to mow the lawn. So your yard can get compacted, which is why they tell you to aerate it periodically, right? This is a big problem, especially on new construction. Because you go out there with new construction, they got these big graders out there, and they're having a great time pushing the dirt around. And they come in and they drive over it again to pour the concrete for the foundation. And they come in and they drive over it again to, deliver the lumber to build the frame. And they keep driving over it. And the last thing they do is they drive over it to put the sod in. So then they lay the sod on top of this really compacted soil. What happens to that sod? It's dead. It doesn't gonna grow. It's not gonna. Soil that it's so compacted that those roots can't penetrate it. So even if you've got a residential property that construction happened 50 or 75 years ago, just over time your soil can get compacted. The compaction of soil can change the property of the soil based on some research that was done to change an A soil into making it behave like it's a C soil. You can change it to hydrologic soil groups. So remember what those infiltration rates are.
It only goes one way though, it never uncompacts.
Okay, so I had this really great sandy soil infiltrating at 0.8 inches. I've driven all over it, and now it's acting like it's sea soil. It's only infiltrating 0.2 inches. The easiest way to get around that is to amend the soil. And what you're seeing now more frequently, and I know of a number of different watershed organizations that are starting to adopt this in their rules, is requiring developers to, as their final step before they sod, to go in and rip the soil, amend it with compost, and then after that's been decompacted, then you can put the sod down.
So they put compost over it, then they work it in,
They
like
work it
with
in,
the
yep.
implement?
Yep. But they just run something that's got tines on it, and it just mixes it right in. So what will happen is they'll come in and take off like the top 8 inches of soil. They'll stockpile that. They'll run this machine with tines. They'll just rip that subsoil layer. Then they'll go into their stockpile, mix in compost, spread it back again using rubber-tired vehicles to minimize compaction. They've got an implement that they can put on it that they'll run over it, in like a hatch pattern. So make sure that it's well mixed and it's well stratified, and then they can put the sod on it. So the test for that is if you can take a piece of rebar that's got a sharpened end on it, and you can just drop it on the ground and it can penetrate in a foot. So that's how they test whether the soil has been decompacted enough.
Penetrate a foot?
Yep.
With no pressure?
Nope, just drop it on.
And a person will be sinking in.
Yeah.
What happens when you open the door and you step on it?
Well, because you're going to put the sod over it.
Yeah, and then you go over it with your little roller.
You get your little roller up on
Okay,
top of it. Right.
Okay. So we're not going to go out in our backyard and do this and have the total come apart because the thing doesn't drop a foot. Go ahead.
So compacted soil. If it's compacted and can't infiltrate, it's going to run off. Some other things that are also influence it, but are things that you're probably not going to be dealing with very much. The slope of the land will influence how much soaks in and how much runs off. Obviously, if you've got a really steep slope, gravity is going to make most of it run off rather than allowing it to sit around and infiltrate. And if you've got a really rough surface, you've got lots of nooks and crannies for the water to get hung up on, so it slows down and it kind of goes off over here, you'll have more infiltration just because it's moving slower. So slope and roughness is really a bigger picture thing than something that you might be dealing with on a neighborhood or a block or an individual parcel. And then the final thing which influences runoff and infiltration is what we call directly connected impervious area. So all impervious area are flat surfaces that water can't get through. Streets, parking lots, roofs, patios, things like that. So in this particular little kind of subdivision here, all that area shown in purple is all directly connected impervious area. Directly connected impervious area means that if a drop of rain falls on the roof, it runs off the roof onto the downspout, onto the driveway, from the driveway out onto the street, it's gone in a flash. So it's directly connected. If you've got less directly connected impervious area, then you have more infiltration and less runoff. So one of the things that you'll be learning about later is how do we kind of break this up? How do we disconnect that impervious area so that we keep more of it on site? We don't make it so easy for it to be all connected up and to run off. That's one of the things that you'll be looking at when you go to a site and you analyze a site is what's that path for that drop of water? You know, can you get it to a green space before it gets out to the street or out to the storm sewer? So let's talk a little bit about how water influences the land. We saw the Grand Canyon. We saw the guy whose house was now only 10 feet from the edge of the creek. Here we've got an alluvial fan that we've got a lot of sediment coming down that river. It's actually creating new land. So water is conveying sediment out into that water body, and it's actually creating new land. Water can tear things down, but it can build things up as well. All right, this is going to be one of the most important figures that you will have seen today. Even more important than the hyetograph. Okay? Development changes runoff. The upper left-hand corner is an undeveloped condition. We've got this nice little prairie out there. It's got some trees. When you think about all the water that falls on it during the course of the year, 40% on average of that water goes right back up into the atmosphere through evapotranspiration. You know, we got lots of trees there, they're using the water, and they're transpiring it. You got lots of prairie grasses, they're transpiring it. You know, you've got some stuff which is evaporating off the leaves of the trees. You've got water that doesn't really have anywhere to go because you've got all this nice vegetation there holding it back. So we've got about 25% staying in the shallow infiltration groundwater zone. 25% is going down to the deep aquifer. So we've got that 25%, which is, again, moving, and it's going to move down to my nearest stream where it's going to give me some base flow. Right? So we've got 25% of that. 10% running off. Really only the really big storm events or maybe the big spring snow melt is running off. All the rest of it's either staying in place, going into groundwater, or it's evapotranspiring away. As you start building more and creating more impervious surface, you change that. You know, you've got somebody comes out there and, you know, maybe they build their house on a big 10-acre lot. They change it a little bit, little less evapotranspiration because they took down some trees. They create a little bit of impervious surface with their house. They're getting a little bit more runoff, maybe a little bit less is going to groundwater. Not big impacts, but it's changing. Okay, now you've got suburbia. You took down all the trees so you could build houses. Okay, you don't have very much transpiration going on, but you've got all these hard surfaces now that you've got evaporation going on. Okay? So you've still got a lot of evaporation going on, but now you've got all these hard surfaces so the water can't soak into the ground. If it can't soak into the ground, it's going to run off. Now we're up to 30% of our annual water running off. And now we're down to only 35% infiltrating into the ground. Now finally, we've built up a big city. We're really, really impervious. We've got no trees there, you got hardly any grass. You got big buildings, lots of impervious surface. You're still getting a lot of evaporation off those hard surfaces. Excuse me, you're getting hardly any infiltration. You've got so many hard surfaces there that the water couldn't go into the ground even if it wanted to. So now you're down to 15% going down to groundwater, 55% running off. So in the natural condition, 50% was going to groundwater, 10% was going to runoff. In the highly impervious, it's just the opposite. You've got 50% running off and 15% going to groundwater. What's happened to the water? What's going to happen to the groundwater that's supposed to be supporting the base flow in my stream?
Is it going to rise?
So under this natural condition here, 25% of your annual water budget is going into shallow groundwater. It's going to move sideways into the stream. Under the really highly developed, it's down to 10%. You've got hardly any water in the superficial groundwater, so it's not available to go in and support the base flow in your stream. Why does Minnehaha Creek dry up in the middle of the summer? There's no shallow groundwater because we've got so much impervious surface that it's all running off the stream. So when it rains, there's plenty of water in the creek. When it doesn't rain, there's none.
So when it runs off, though, is it not running off into storm sewers that go into the creek?
Yep. We're really good at getting rid of water.
Well, I guess my question is, so, I mean, I'm not saying, oh, it shouldn't matter, but I'm trying to think, so if the base flow is not there, well, are we just not returning it to the creek a different way, through pipes instead of through the ground?
Except that we're changing the timing. So if we've got lots of groundwater, that groundwater is there on a sustained basis. Runoff happens when it rains. So if it rains once every 2 weeks, you've got water in the creek every 2 weeks, and then it goes away.
But some creeks naturally are seasonal, right?
Yep. Mm-hmm. Right. We call those intermittent streams. So, for example, prairie streams are usually intermittent streams because there's so much infiltration. They've got all these prairie plants. They've got these hugely long roots that it's really, those are direct conveyances down really into the deep groundwater. So it's not going to the small streams, so they're going dry during the summertime as a natural condition. This is important. It's very important that you not only be able to understand this, but you're able to explain this to other people, which is why I'm going to give you a writing assignment shortly.
As far as those numbers, is there a way we can get back to this some?
It's in your pack. It's in this little binder here.
Yes.
Excellent.
Yep. This, not only is this important, this is a very famous graphic. You'll come across this all the time. Okay. All right, last couple of things. You know what a hyetograph is, right? Just shows the precipitation over time. Another thing that we're interested in is a hydrograph. A hydrograph shows the movement of water during and after precipitation. So, say we're interested in a 24-hour period of time. We're going to look at how water moves in that 24 hours. So our x-axis here is time, starting at the beginning and going to some point in time. Our y-axis there is increased rainfall and increased runoff. So it's an amount that increases as it goes up. So we know what these blue bars are here, right? What are those blue bars? That's a hyetograph of a rainfall event. So it rains. Okay, so at the beginning of our time that we're interested in, it rains. Bum, 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 bum. In this particular location, we don't really have any runoff yet. It's raining. It's, rain's kind of caught up in the streets. It's, ponding in the backyards. Some of it's infiltrating. It's not very much of it is running off yet. But eventually, there's going to be enough rain accumulating that it's going to start to run off. So you can see that it's raining, it's raining, it's raining, it's raining, nothing's happened, and then all of a sudden we start getting runoff. All of a sudden you'll start seeing rain running in the gutters. Okay? And that amount increases and increases and increases over time. And at a certain point it's going to hit a peak. So the time between this peak and between the peak runoff and the peak rainfall, we call that the lag time. How long after the most intense rain happens do we see the most runoff happening? That's the lag time. And then, after a while, that runoff is, the storm sewers are very efficiently carrying that runoff down to Minnehaha Creek or wherever, and eventually it all goes away and that runoff starts falling again. So we have a rising limb and a falling limb. So we've got important things in here. We've got peak rainfall. There's a lag time between when we have the peak rainfall and the peak runoff.
The runoff slowly increases, reaches a peak, and then it slowly decreases. We're going to compare that. So here's another hydrograph. This is the impact of urbanization on stream flow. So here we've got our precipitation hydrograph over here again. So we've got a rainfall. Here we've got time going on. In our nice prairie, where we only had 10%, or maybe we might have a big lot development out there, and maybe we have maybe 12 or 15% runoff. The lag time between the maximum rain and when you get the maximum runoff is long, because you're not getting very much runoff anyway, and it's taking just a long time to accumulate to the point where it's going to reach a maximum. You can also see that the maximum amount of runoff isn't that much. So now this blue line right here is what happens when you're in an urban setting. So remember, in an urban setting, we had less infiltration. We had much more runoff. And that much more runoff is also being conveyed really efficiently across our gutters and our storm sewers. And what's happening is that this lag time now is really short. It doesn't take very long after the rain really starts getting going before you start seeing runoff happening. Not only that, but look at the difference in the peak. So you're faster and you're higher. That's the impact of urbanization. In this particular case, we're looking at stream flow, the amount of water in the stream. We have the exact same effect if it's just looking at just runoff in your gutter, runoff in a channel, or some other conveyance. When you're urbanized, you get higher peaks, faster peaks.
I noticed as they've been, doing street work in my neighborhood that they have taken out some of the stormwater sewers. So they, it seemed like there was one on every side of our block, and now they've taken them out. Is that because of to try and decrease how fast it's going into the creeks, or
are they putting in larger pipes?
They did do some of that, yeah, when they took up the street.
They could be doing that. Are they putting in underground storage?
That I'm not sure about.
Okay, that's something that's new that's happening, especially in really dense cities like Minneapolis. When they take up the streets, under the streets, they'll put these big pipe arrays, so that when the stormwater goes into the storm sewer, goes down, and it's stored in this gallery of pipes. And it's just held there until it's released at a later time. And that's a way to reduce that peak, so that it's discharged from that in a more measured way.
So there must be some hydraulics that probably prevents it from going. I mean, it just times it so
yes.
It comes out.
Yep.
Okay.
Yeah, that's just the way it's the way the outlet is designed.
But it's still eventually.
It will still eventually get there, but it's a way to slow down the rate that it's going. Go ahead.
Oh, okay. On your graph, the Y, the stream.
Mm-hmm.
What stream is it? The runoff stream, or what stream were you? I'm sorry, I missed that point.
This graph. There's just a graph that's showing in a river, a stream,
a proper stream.
Right. But really, it's a stream. It's any type of moving runoff that's happening.
Any type of moving.
Yeah. Yep.
So we've been talking mostly about urban here, and yet in agriculture.
Oh yeah, I've got a picture for you.
Well, I mean, most fields nowadays are drained, and so the lag time is shorter. So there's a similar process going on, and they run more water into the ditches, into the streams, and down the Mississippi.
This is the Soybean Council. La 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 la.
Okay.
Yes.
There's always been a conservation movement, more potholes to some extent, or, things like that, but is there much going on that's really effective?
There are some things that can be done to hold water back in the fields during certain periods of time. The problem is agricultural fields are tiled to maximize their ability to be used for farming, right? So the time when you really need to hold it back is exactly the time that you want to be using it to grow your whatever commodity that you're growing. So if you are in the middle of the spring planting season, okay, you want those fields drained as quickly as possible. You don't want your seeds sitting there in super wet soil. So you want that tiling to get all of that out of there right away. But at the same time, now you're making that runoff get down to the ditch or that stream, down to the Sauk River or the Crow River. You want to get it out of there into that river as fast as possible. Now that's causing problems in the downstream river. So the way to solve the problems in the downstream river or ditch or wherever it's going to is to either remove the tiles or to put a gate on the tiles so it can't discharge. That leaves water in the field. So we're kind of at a catch-22. So that's what they're trying to figure out is there a way that we can manage those tiles at least a little bit so we can do both things?
Well, there's got to be. It's as simple as can be the method they use, and it's just tiles stacked one against another to make a pipe with. So you think they could put a gate in it pretty easily?
Yeah, and you can, but again, it's something that has to be managed, and they're not real expensive. But if you've got 40 acres of tiles and you've got 10 tile outlets into the ditch, then it's $2,000 times 10. Then you're talking about money. So you're right. We're talking urban stuff. Same thing applies in agricultural areas where there's a lot of time. All right. So, what are the impacts of development on streams? This is a stream. Looks pretty nice, doesn't it? This is, I don't remember where this is located, but it is upstream of the city. You can see it's really nice. Got nice stream banks. Got some good flowing water. You could probably catch some fish there. You got all kinds of aquatic life in there. This is the same stream in the city, so it's downstream of the city. What is it that makes that happen? High volume. So we're just sending lots of water there. It's fast. Okay. We're sending lots of water there. It's not only going there fast, but it's lots of water, so it's rising up really fast.
And it's collecting stuff.
Right, and it's collecting stuff. There's a lot of power in it. It's making those stream banks really wet. What's on a stream bank? Is there stabilizing vegetation on that stream bank? No. Not at all. Okay. A lot of times when you're in the more developed area, you like to mow right up to the edge of the stream, right? Okay. So you don't have any stabilizing vegetation on the side there. Big storm comes, woof, this bank falls right in. I'm wearing new shoes. They're not broken in yet. My feet hurt. Impacts of development on water resources. So kind of generally, urban flashiness. It's that change in the lag time. So we've increased the lag time, we've increased the peak. We call that being flashy. Water comes and it goes. Okay? I will show you some pictures of what I mean by flashiness. Okay? Urban runoff and flashiness. Okay, this is Shingle Creek in Brooklyn Park. We just had a 2-year, 3-hour event, so it was something like almost like 1.8 inches in 3 hours. So if you can't see in the back, got a nice development up here. Here's the creek. Here, along here. One thing I want to point out to you. Okay, you see this pedestrian bridge? Okay, you see there's maybe about a foot between the pedestrian bridge and the top of the water? All right. 2 hours later. 2 hours later. Okay, where's the water in relation to that pedestrian bridge? Okay, you see this line of debris? Oh, hello. See this line of debris? That's where the water was. That's where the water was.
Oh my God.
That is an urban flashy stream. Okay. Now, when they built this, they knew that was going to happen. So they sloped those banks back so that they could accommodate those large flows. But still, that was a 2-year event. That wasn't a 100-year event, that was a 2-year event. All right, so we've got urban runoff and flashiness. We already talked about it several times because it's something that, as a stream ecologist, is just really bothers me, is a decrease in stream base flow. Think there's any aquatic life in that stream?
Not anymore.
Not anymore. Would you like that to be in your backyard for 3 months out of the year?
It is.
Yeah. There you go. You know exactly what I'm talking about. Yeah. So this is not good. But this is what happens when you decrease the amount of infiltration so you're not getting a base flow in that stream. The other thing that's happening here that's maybe not quite so obvious, one of the reasons why there's hardly any water in there is look how wide it is. Okay? That's a constructed channel. That's not the natural channel. That's been dredged and constructed. They made it really wide and nice and trapezoidal so that it can carry the 100-year flow. That increased 100-year flow that came because of all the impervious surface and all the storm sewers dumping water into the stream. During the 100-year flow, it's full of water.
Right.
You know, like that picture that we saw. All the rest of the time, there's just a little trickle of water going down through the middle of it. We've made these channels over wide because we've built them. We've engineered them to carry the highest flows that we can send to them. Some other things that happen, we've got changes to wetlands. The same way that we're not able to support stream-based flow, wetlands are sustained by water from groundwater. We reduce that groundwater, we're getting less water to our wetlands, so we're changing our wetlands. We've got stream bank instability. You already saw some photos of those stream banks that were falling in. Talked about before about agricultural streams. Same thing happens in agricultural streams. So all those changes that happened on that graphic about increasing the amount of runoff, decreasing the amount of groundwater, are all causing these types of things to happen. Okay. So, 2 years ago, I did a project in the city of Davenport, Iowa. Davenport, Iowa is bisected east to west by a stream called Duck Creek. City of Davenport owns a corridor, like what the park board owns along Minnehaha Creek. City of Davenport owns a corridor along Duck Creek. A lot of parks right up against it. It's kind of their park and recreation corridor, right through the middle of the city. They got some erosion problems. Okay. This is my colleague Jeff. Jeff is saying that I'm going to take this picture, I'm getting out of here. Maybe which doesn't come across in this photo is, all right, Jeff's, maybe about 5 to 8 or so. So you can tell that this is maybe about a 12-foot bank we've got there. All right. First of all, you can kind of see that a whole bunch of soil has just fallen right off there and created an indentation of that's about 3 feet deep. Okay, we've got an overhanging lip that's about 3 feet over here. Okay, he's standing there underneath that overhanging soil with nothing holding it there except a few roots. And these little orange dots here are things that we call bank pins. Those are things that we put in the bank to monitor how much erosion is happening in a bank. Basically, it's rebar because we like our rebar. And you take rebar and you spray paint it orange, and then you drive it into the bank horizontally, and you leave some of it sticking out. And you measure how much of it is sticking out. And then you GPS it so you can find it again, and you spray paint around it as much as you can so you can find it again. Then you go back periodically and you say, well, we left it at 2 inches sticking out, now it's 3 inches sticking out, so you know that you lost the stream bank. So he's there pounding that rebar into that overhanging, he's going, I don't want to be here, I don't want to be here. Just take this picture, get me out of here. This is taken on the west side of Davenport before all the urban runoff, all those storm sewers are being discharged into Duck Creek. Upstream of that is agriculture. Tiled cornfields. It was Iowa after all. So all of that runoff that's sufficiently flashy to erode that stream to get a 12-foot cut bank like that is coming from agricultural fields. Urban flashiness, agricultural flashiness. I'm not going to have you do these assignments in class because we're getting close to our time, but I would like you to write an assignment down in your journal, and then you can finish that on your own and bring it to the next class. So writing assignment number 1 is to write a paragraph that describes how does development change where precipitation goes, and how does that affect our lakes, streams, and wetlands. And when you write your paragraph, you can feel free to consult your notes, and hopefully by then the presentation will be posted on the website. So the purpose of this writing assignment is just to see whether you're able to take this information and synthesize it into just a short description. So if you had to write a paragraph, say for a newsletter or for a website, could you in one paragraph answer that question? Everybody got it down?
Yep.
Okay. All right, we're going to wind up just talking a little bit about observed climate changes. You can see that I call it observed climate changes. I did not call it climate change. As an individual, I believe that we are experiencing climate change, but the extent and nature of that is yet to be, I think, agreed to. But we have observed a number of things in our data that leads us to believe that there is something very specific going on. So, information that's been compiled by the State Climatology Office. First of all, Minnesota average annual temperature. Going back to the start of the official record in the 1890s, and actually Mark Seeley's got some even older data that he's put together. You see that there's been kind of a gradual increase. There's been a 1.6 degree Fahrenheit change over the past century. That increase is accelerating. So just within the last about 25 years, there's been an acceleration in that average annual temperature. If the whole century had been changing at that rate that we've observed just in the last 25 years, that would have been a 3.4 degree Fahrenheit increase in the average annual temperature. That's pretty significant.
the average minimum temperature December to February. Doesn't seem like that sometimes, but the data is showing that our nights are warmer in the winter now than what they used to be. So that over the past century, there's been an increase of about 3.5 degrees Fahrenheit. But again, within the last 25 years, that's really accelerated significantly. If the whole century had been changing at that rate, that would have been an 8-degree Fahrenheit change. That's a really significant change. Yeah. So we've got warmer winter nights. Here's our kind of our state average annual precipitation. You can kind of see that there are some dots bracketing the 25th and the 75th percentile. But you can also see that in the early part of this period of record, you only had a few instances when the annual average was outside of that 25 to 75% range. As we're proceeding more into the latter part of the 20th century and into the 21st century, you can see that we have many of those annual average precipitations, which is falling above the 75th percentile. And we've got fewer and fewer drier years and more wetter years. So we're seeing that change. That line is the running average. So an individual point says, this is the average of the last 7 years. So it kind of evens out some of those, year-to-year variations. And here we've got the Dust Bowl. So you can see that we kind of had a big drop here. Now we've got a trend that's moving definitely up. So we're getting wetter. And we are having more and more years that are wet versus years that are dry. More precipitation, warmer temperatures, warmer winter nights. This is a crazy, crazy graph. And I'll try to explain it because it is saying something interesting. It actually took me a while looking at it to try to figure out what's going on here. So we've got the 4 seasonal quarters. Winter over on the upper left-hand corner, December, January, February, spring, March, April, May, summer, June, July, August, fall, September, October, November. So we've got a period of record there going back to 1895 and going through 2010. And that line in the middle is the average. Okay? So the average amount of precipitation during those 3 months. Where you see those green blobs, that means that precipitation that month was above average. Where you see kind of the brown blobs, the precipitation that month was below average. So if you look at winter, you can see that it kind of goes through periods of, well, it's below average, then it's above average and below average and above average, but for every below average, there's an above average, and it's kind of, some variability to it. Those peaks are getting peakier, okay? So we're still kind of going up and down in the winter months, but we're getting bigger slugs of precipitation. So now let's look at the same thing in spring, where we've got kind of up and down, but now our ups are even longer. So we've got a really short below average, but now we've got an even longer and higher above average. Same thing. Now we've got this really long period of above average in the early spring. And now in the summer, we've got variability that's going on, but we're still variable, but they're about the same, above and below. So it's not really changing a lot in the summer. But in the fall, whereas we used to have a whole bunch of below average, now all of a sudden we've got a whole bunch of above average falls. So our rain is falling at different times during the year. We're getting more big events in the fall. Okay? We're also getting more big events in the late winter. So if it's February and you're getting a big rain event in February or March, what's happening to that rainfall? It's running off, okay? Or if you get a big snowmelt event and you've got a whole bunch of snow and you get a snowmelt event,
It's running off. And we didn't used to get these really late fall storms. Now we're getting a bunch of fall storms. So there's a changing in when that precipitation is occurring. Not really quite sure what that means yet, but definitely if you're getting a lot more big events in the late spring before things have really thawed out, when you get that precipitation, it's not helping you much because it's running off. Same thing if you're getting a lot of big precipitation events at the end of the growing season, that's not helping in your growing season. So it kind of took me a while thinking about what that meant, but I think there's something there. Okay, dew points. Has it been muggy or what? There has been a documented increase in number of dew points greater than or equal to 80 degrees. So if it feels like it's been muggier, it has been. So one of those red triangles indicates where that location has had 10 or more days with dew points at 80 or higher.
80.
An 80 dew point, I mean, you know what an 80 dew point feels like, right?
Yeah. I remember that.
You remember that, right? So, so there's an increased amount of dew point. There's more saturated water in the air, right? We've got bigger rain events. We've got more water in the air. We've got warmer temperatures, so that because we've got warmer temperatures, that air is able to hold more water. That's why we've got higher dew points.
It's a very curious pattern of distribution.
It is, isn't it? And what's interesting is that we're starting to see it happen way up in the northern part of the state. And if you're interested, if you go to the climatology website, there is some information in there about observations regarding changes to the plant communities that they're starting to see now in the northern forests, where it's changing, some of the plant communities changing the type of trees which are flourishing. And it's also, as you've probably heard, it's because we've got warmer temperatures, it's allowing some of the pests, the insect pests, to move further north. Now they're being more of a problem.
Termites in Minnesota.
Yeah. So that's one of the issues with warmer nights during the wintertime. We're not getting long periods of cold temperatures to kill off those. Right. So, potential water resources consequences of observed climate changes. Let's take the last 5 minutes here just to talk about what we think that means. So we've got bigger storms. We're seeing them changing when they're happening. We're seeing higher dew points, higher temperatures. What do you think that might mean for our water resources?
More.
So let's think about lakes. More evaporation.
More runoff.
We've got more runoff with more pollutants.
Warmer temperatures.
Warmer temperatures. Algae thrive in warmer temperatures. So when we've got those pollutants being conveyed to the lakes, now we've created these great environments for the algae to grow in. So what's likely we'll see some increased degradation in our water resources. Okay. We're having events at different times of year so that it might be disrupting aquatic life. So if you're getting a lot of big flashy storms, for example, during the time when the fish are laying their eggs, you may have more mortality of the eggs, so you won't get as good of a I don't know what you call them, crops of fish.
Rising sea levels.
Rising sea levels.
Well, that naughty bug is in 86 degree water or higher, so it's called everybody better be wearing nose plugs because they're in every body of water.
Right.
People just don't know.
The bacteria whose name I can never remember.
But yes, it thrives in warmer waters. We've got warmer waters. We'll have different types of aquatic vegetation that thrives, different types of bacteria. We might see more blue-green algae blooms. So, there are some really significant consequences, even beyond just we got more rain and we need to deal with it. So we're changing our biota, we're changing water quality. And additional impacts, we're having some changes on when plants bloom. We're changing when our temperatures are occurring. Lots of different ways that can affect our water resources. Going beyond just the fact that we may be seeing more rain. So your final assignment for you to do and bring back to the next class is to think about that. And how would you talk to your neighbor or a friend of yours who's maybe a little bit skeptical? And how would you explain to them what's being observed? What does that mean? Is that going to have an impact on their property? And it might help if you've got somebody specific in mind when you write the paragraph.
So this is one of those letters you write but don't send?
Delete. I did press delete and not send, right? So if you've got that down, I'll put it back up. But reflections and final thoughts. We got 6 minutes. Let's take 3 of them. I have 3 volunteers. Tell me one thing that you learned today that you didn't know before. Come on, volunteer, or I can call in somebody.
Hyetograph.
and use that in conversation in the next meeting. So a hyetograph, a record of precipitation.
And how to calculate runoff.
Okay. How do you calculate runoff?
The explanation of what return.
Area times rainfall.
Okay. Area times rainfall. And you might have to put in a correction factor or a
Yeah.
conversion factor in there. Okay. So you might be, how many gallons in a cubic foot?
7.5.
All right. Another volunteer, what's something that you learned today?
Concept of the return period.
Okay, so if somebody says to you, what's a 100-year event? What does that mean?
It's the 1% chance of that amount of rain falling.
Well, that can't be right. They said on the TV that we can have we had 3 100-year events this year. You're not role playing with me.
We've only been to one class. We're adjusting that.
Yeah, there you go.
You can flip a coin 5 times and get 5 heads. It's just a probability.
Yeah.
So it doesn't mean it's not guaranteed that it'll only happen once every 100 years. It just means on average, we just happen to have a really non-average year. Right? Okay. One more.
Atlas 14 and TP40.
So what are they? Wow. What?
TP40 was the old calculation for the 100-year, and 10 and 2, and Atlas 14 is the new calculation.
Okay. So when was TP40 published?
1961.
No, TP40.
Oh, TP40, oh, that was 61.
1961. Okay. And Atlas 14 is this. Okay, one more. I saw another hand back there. Somebody else had one here. Come on, one more. Go ahead.
Oh, it was her hand first. So You're the one who raised it before, so I'll let you answer.
Oh, I actually have a couple questions. First one was really actually just thinking about how a big impact you can make with putting your rain garden in your yard and improving infiltration. I mean, we live in the middle of the city where there's almost none.
Mm-hmm.
So every single yard makes a big difference.
Yeah.
So that's one observation just from today. The other question I had though was the question back to how come we had 300-year events in the last year? Doesn't your graph about the observed change in actual rainfall variation from normal, doesn't that indicate that we'll continue to have those kinds of events?
Yeah, what will happen is that we'll just redefine what a 100-year event is.
Yeah, okay.
Atlas 14 is doing that, or it's not?
Yeah, it is. All it's doing is saying that, well, based on the data, we thought the 1% probability was 5.9 inches. Now that we've got more data, now we realize that the 1% probability is 7.9 inches. It doesn't, and that takes into account the actual precipitation, and some of that precipitation seems like it's increasing. But the mere fact that Atlas 14 is different from TP40 doesn't necessarily mean that there's climate change happening. It just means that we've got more data and we're more accurate.
So the climate change is really more reflected in that quadrant.
Yes, right.
That you showed at the end by the season.
And so we've got that last 25 years where now it's kind of going up faster than it was before. As that period of record extends, and we're looking at the longer period of record, we'll start seeing more and more of those big events. So we might find out in 30 years that the 1% of the 100-year event might be 8.5 inches. But you really only care about the 1 inch. Any other questions?
So I have a question on that, those graphs that were showing the levels of ET and runoff and shallow infiltration and deep infiltration. There. And then we talk about base flow. Is base flow the shallow infiltration?
It's a shallow infiltration. The deep infiltration is the infiltration that's going down into the bedrock, down into our deep aquifers.
So, in talking about global warming, we were saying that we're getting more rain, more precipitation, and bigger events. And part of that is because the atmosphere can hold more water. And it's holding more water because the higher the temperature, the more evaporation and transpiration that happens.
Right. It's both because there's more evaporation, more transpiration, and also because warmer air can hold more water. So it's both happening.
I just want to put an invitation out there. There's a documentary that just came out called The Price of Sand, and it's about mining for fracking sand, and it's quite extensive in Wisconsin. It's being debated in the Minnesota legislature right now. The movie will be playing at the Riverview Theater Wednesday, May 1st at 7 o'clock. Please see it. It's important because the debate actually affects our water resources, not to mention our land and air resources.
Yes, sir.
Is there a makeup session at all?
I don't know. Is there
For this class?
Yes, for this session, because I personally didn't feel like I got any information that I can take home and probably feel like I learned something today.
We don't have a makeup session planned, but that's one of the good things about the website that will be launched next week is that you can have forums so you can talk to other people, because I know there's lots of people in here that probably feel like they didn't learn as much as they wanted to or could, and you can always email us and ask questions, or just talk to your classmates and see if they have an answer.
The way that these classes are set up is that they build on each other. So the next class is actually taking these same concepts and extending them even further and talking about, well, then what does that mean for water quality and what kinds of practices can we do? So there will be a review of this information as part of that.
Yeah. Yeah, so all of the sessions that are being filmed will be posted on the website.
It is a lot of information to take in at one time. You've got the highlights of a semester-long hydrology class tonight.
So feel good about yourself. Really, you infiltrated more than what you think right now. So at the next session, when Shane starts talking, Shane Asagi, who's the instructor, the next one starts talking about this, it will come back to you. They'll say, oh, that's right. I remember Diane told us this. So if you've got further questions, you can send them along to the instructors and they can either answer them or they send them along to me. Thank you so much for coming. I'm really excited about this.